It'd be good if you've watched the two t-test videos. This is the second case where you have paired data. If you have paired data, then correlation can be used as well as a tool of analyzing what's going on. Paired data means that Dave here took a test on how much he could squat. He got 61. Then he did 4 weeks of training, and then he went up to 77. And we've got 20 different people who've done the same. Notice the 20th person here got worse, but most of them have definitely got better. And for this type of data, we should use a paired t-test to provide evidence that 4 weeks of training does make a difference for all people, not just for the 20 people in the sample, but for all people. And for t-tests, we're always making claims like that about populations. However, correlation, we are just looking at the correlation of this data. So let's nip over into Excel. So we're just let's first of all look at it. So you select the two columns. Be really careful here. You want the titles. You don't want any junk on the left. You don't want any like averages or anything like that. Be really careful to choose the correct stuff. Insert, and then you'll see various things. The easiest one is this one. Scatter, and then choose one without any lines on it. And there's my scatter graph. Already it's not looking like great correlation, is it? Now, we're not happy with that. It's a messy diagram, or it's a poor diagram. Let's just add a couple of things. Quick layout. Go to this one. And it provides all kinds of stuff. So for a start, it puts titles on. This was before. This is after. So after 4 weeks training, before it. I'm going to move this out of the way. I don't think I need a legend. That's all looking nice. I've got this huge wasted space here. So I'm going to double click on any of the numbers. And it says from 0 to 100. No, let's go 50 to 100. And then the same here. I've got nothing below 60. So let's not waste space. Let's go from 60 to 140. And then this is my data with a correlation on it. And it tells me what the R value is. But let's just ignore that for a second, because visually you can look at correlation. Is this correlated data? No, it isn't. It's an absolute mess. And you can see that the R value is really small. This is technically R squared. So the square root of that is still a very, very tiny number. There's no correlation. Now that's no problem. Not every IA will have correlation. I would put this scatter graph in, and I would show the correlation, which is this here, but I would not include this line. This is the equation of the line of best fit, which is better called the regression line and could be used for predicting. So if you, before you could bench 80, I think it was squat 80, then after I would expect you to squat 95. Well, that's no good because there's no correlation. So you should not include a line of regression if there is no correlation. Looking at some completely different data, age against your 10K time. Let's do the same thing. So I select it, insert a scatter graph, and then click on it and go to quick layout, add all the stuff apart from the legend. Make sure you fill in the axes, titles, and things like that. Put that somewhere it can be seen. So now we're looking at a data that does look correlated, not amazingly actually, and sure enough the R squared value is not amazing, 0.5. You should square root that to find out R, or you can just simply in here say equals correl. That's the correlation coefficient of that lot, comma, that lot. And that is 0.725, which is the square root of that number. So that is what I would call moderate correlation. Anything above 5 but below 0.9 you'd call moderate. Anything above 9 you'd call strong. And if it's really quite high, then you say very strong. You should definitely put this graph in your IA and talk about the anomaly. If there is a nice clear anomaly, what's happened here? This is a 45-year-old who's just really slow. And one thing you should get right with correlation is which one is the x-axis? This is age, and that is time. Which would you expect to cause one? Now, if there's any chance that one is causing the other, then you should have it on the x-axis. Now, clearly age is a factor here that may help us predict how fast you're going to be. So age has to be on the x-axis. So it is the x value in this equation here. Now, because the R value, 0.725, is reasonable, we can use this as a predictor. So a 35-year-old comes along, then he will say, well, we can use this. I would estimate your 10K time is going to be 12 point something minutes. You're not saying this with huge confidence because the correlation is not super high. So this is what correlation is used for. It's not used in hypothesis testing. If you want, this one is not valid for a t-test, although it is paired, as in this is one person who's 18 and ran at that speed. It isn't to do with it, improvement. These two things not measuring the same. I go back to the squat test where we had a before and after. This one, we tried some correlation, and the correlation didn't really work out. We got effectively zero correlation. But this one is very good for a paired t-test. Okay, cheers.